Hello everyone and welcome to the session on essential mathematics for test engineers. I'm Sundaresan. I work for IBM as a test architect. So imagine that you are actually testing an omni-channel feature, a feature that actually cuts across different operating systems, different devices or form factors. Imagine that you're actually testing a payment page where there is credit card, debit cards, UPI, and several other payment methods. Imagine you're testing a business rule. For example, you're testing a shift scheduling algorithm, which actually lets an employer schedule shifts based on an employee's availability or their skill sets, or even based on the requirements that they have at that moment. And imagine you're testing a semiconductor where there is a lot of logic that is involved. So in all these areas, you'll have to apply test design and also you'll have to apply a lot of test logic, isn't it? So mathematics is essential, absolutely essential for you to kind of apply design as well as logic in your day-to-day testing. So I'm going to take a couple of areas in mathematics and just go across a few definitions and then see how it actually helps you on a day-to-day basis. So to begin with, does these terminologies actually ring a bell? Collections, data types, collections of objects, combinatorial testing, orthogonal array, equivalence class for datasets. All these actually involve testing and even coding for that matter. You may use it in your automation or you may use it in your test design or test planning. So which area of mathematics actually deals with data or grouping of data? It's nothing but the set algebra. I'm sure you would have actually read set algebra in your pre-high school or maybe even high school. Set is basically a collection of objects known as elements. So here are a few examples of set. So there is a first set which is V, which has got strings, cat, dog, fish, and then W, which is numbers 1, 2, and then X has got odd numbers 1, 3, and 5. And then the final set Y is basically a notation that starts with N, and N is an odd integer, and integers contains both negative as well as positive numbers. Further defining the sets, if a particular element belongs to a particular set, then it is actually denoted by a notation, the vague symbol which resembles the letter E. And then sets can be finite or infinite. And the symbol phi or 5, as you may call it, denotes the empty set, which is in this brackets, and then which does not contain any elements. Of course, it's an empty set, right? So moving on, so B and A are actually the sets that are actually represented in this roughly elliptical shape. So A is a fairly larger elliptical shape that you can actually see here. So A is, we can call it as the superset, and then B is basically contained inside the A set, right? So we can call it as subset. So if you look at it, the elements of B are nothing but these two stars you can see, and then elements of A are actually these three stars that you can see. But since B belongs to A, these two stars that you may see inside the B subset also belongs to A. So the total number of stars that you may actually attribute to A is about 5. Whereas B, since it's a subset of A, we cannot claim the stars outside its boundary. So it's just the two of them. The next definition, which is Cartesian product. So Cartesian product is nothing but I'm going to actually multiply or marry the elements of two different sets. So in this case, the we'll try and find the Cartesian product of A into B. So the numbers 1, 2, and 3 belongs to A, and the characters X and Y belongs to B. So how do we define the Cartesian product? So in this case, you can see 1x, 2x, and 3x are the Cartesian product of A, and then again we'll have to multiply the same numbers with y as well. So 1y, 2y, and 3y makes it a complete Cartesian product of A into B. So in this case, if an element of element of lowercase a belongs to A, and then lowercase b belongs to B, you'll have to actually multiply A into B, and that's how the Cartesian product is formed. An intersection of set is nothing but, let's say there are two sets, and then I'll just go ahead and find the elements that are actually common to these sets. So let's take the example 2, 4, 6, 8, 10, and then which is the set A, and then the set B has 1, 3, 8, 4, 6. So I'll have to find the elements which are common, and in this case it's 4, 6, 8, and then A intersection B is nothing but the common elements, which is 4, 6, and 8. And if you go to union, here I'll have to just combine both the sets. So the elements of set A is 1, 3, 7, 5, and the elements of set B is 3, 7, 8, 9. So when I create a union of both, it will be 1, 3, 5, 7, 8, 9, which is nothing but a combined set of A union B. Now, where can you use set algebra? Of course, while forming your equivalence classes, you can use an empty set as an equivalence class. Also, you can derive at a superset and a subset to actually come up with a set of equivalence classes that you may need to test any of your fields. And then while testing a credit card, I'm sure there are multiple combinations of credit card or credit card numbers that you may want to test. So I'll take a very simple example where you take credit card as a superset, and then you take Master Visa Amex as a subset, and then you go ahead and create multiple other subsets for maybe banks and countries and things like that, and then start marrying each set using the Cartesian product, and you will basically evolve a Cartesian product of all sets. Feature relationships. So say for example, you have a huge system which has so many features cutting across different areas of the software. Then how do you evolve the intersection of features? How do you know that if I touch this feature, it will affect the other feature in some other area of your software? So to kind of build this, you can actually use your intersection and union evolve the intersection and union of features. Okay, the next area that I want to touch upon is truth table. Truth table is basically a chart that shows the truth value of one or more compound propositions. Propositions are nothing but statements. You actually use a combination of statements and then say, hey, for these combinations, what should be the outcome? So let's take an example and try and understand. So in truth table, you basically validate the arguments, right? So let's take, for example, you have a feature configurator and you have two rules, which is combined in the same sentence for ease of use. So let's say if, for rule P, when X is checked, and for rule Q, when Y is checked, feature A must be available. And then for the rule P in the second case, when X is checked and or when Y is checked, feature A must not be available. So yeah, how does it actually, how do you validate these arguments in a truth table? You actually just construct a table and then say, hey, for the first example, which is true, when X is checked as true, and then when Y is checked as true, then the outcome must be true. And if there is any other outcome where one of the options are actually unchecked or both of the options are actually unchecked, then the outcome must be false, which is basically in our case, the feature may not be enabled. In the second case where we saw an or, if either of the or what is that business rule is actually checked, which is say for example when X is checked or when the Y is checked, then you just go ahead and say, hey, the feature must be enabled. So when P or Q is T is going to be true, and then either P is T or Q is T, then you are still going to be calling it as a true value. But when both options are actually unchecked, then the outcome is obviously going to be false. So finally, a couple of websites where you can actually read more about algebra of set. facts and truth table. Hope you can actually jot it down on a paper and then continue reading and expanding your mind. Thanks a lot.